Hi everyone, my name is Josh Robbins, and today I will be presenting our paper, Efficient Solution of Mixed Integer MPC Problems for Obstacle Avoidance Using Hybrid Zonotopes. First, I'll mention that this talk will include methods and results from a journal paper submission we have that extends our CDC paper, and that paper is titled Mixed Integer MPC-Based Motion Planning Using Hybrid Zonotopes with Tight Relaxations. And it is available on arXiv using the QR code here. So we consider the problem of autonomous vehicle motion planning with model predictive control subject to non-convex obstacle avoidance constraints. And this is challenging in general because optimizing with these non-convex constraints results in NP-hard optimization problems. And in practice, often it is not tractable to solve these optimization problems fast enough to apply them to an autonomous vehicle motion planning context when using MPC. So approaches to mitigating this problem include, and this is not an exhaustive list, custom solvers for autonomous vehicle motion planning, and the use of advanced set representations, namely zonotopes and their extensions, to represent or reduce the complexity of the non-convex constraints. So we take a sort of hybrid of these two approaches. So we represent the non-convex constraints using hybrid zonotopes, which are an advanced set representation, and exploit the particular structure and properties of these hybrid zonotope constraints within a custom MIQP solver tailored to autonomous vehicle motion planning problems. So what is a hybrid zonotope? So in this graphic on the left, we have an autonomous vehicle navigating through a non-convex free space, which here is partitioned into 12 convex polytopic subregions. And we can represent the union of these 12 polytopic subregions as a single hybrid zonotope. And the equation for a hybrid zonotope is given here on the slide. So hybrid zonotopes implicitly represent unions of polytopes using both continuous and binary variables. So they're a mixed integer representation. And we developed a custom MIQP solver that exploits the structure and properties of this particular hybrid zonotope representation to solve these autonomous vehicle motion planning problems more quickly. Specifically, exploiting the properties that the hybrid zonotopes have tight convex relaxations, meaning in this case that the convex relaxation is equal to the convex hull. And this allows us to construct QP subproblems that are tight and that allow us to converge in fewer branch and bound iterations. Additionally, we exploit the fact that using these hybrid zonotope constraints, all of our inequality constraints are box constraints. And using a particular QP solution technique, this allows us to reduce the number of matrix factorizations that we need to solve when solving the QPs. And that allows us to solve QP subproblems that we're generating in this branch and bound mixed integer solver more quickly. So how do we represent the obstacle free space as a hybrid zonotope? We have two different approaches we take. In the first case, we start with a union of vertex representation polytopes. And in that graphic that I've been showing, this is what we do. So first, we partition the free space using partitioning algorithm. We're using the Hertel and Melhorn algorithm. And then we use theorem 5 and reference 2 at the bottom here to construct a hybrid zonotope from that vertex representation partition. And that results in the figure you see here. And then additionally, we consider the case that the free space is represented with an occupancy grid map. And we would do this because occupancy grid maps are widely used in robotics. So an example here is this figure on the right, where we have dark gray rectangles that denote occupied cells and light gray rectangles that denote unoccupied cells. So it's a grid. And we can represent the unoccupied cells directly as a hybrid zonotope using these matrices and vectors that I'm defining on the left side of the slide here. And one thing to note here is the number of equality constraints and the number of continuous factors in our hybrid zonotope description does not scale with map complexity using this formulation here. So for both of these free space representations, it turns out that the convex relaxation is equal to the convex hull, right? So these representations are tight or sharp. And this is an important property when you're going to solve a mixed integer program, because when you solve mixed integer programs, especially using branch and bound methods, you end up taking a series of convex relaxations, and having those convex relaxations be tight to the non-convex set, as they are here, allows you to create a better representation of the problem that you're trying to solve and converge in fewer branch and bound iterations. So we say that a set C is mixed integer convex if it represents the feasible space of a mixed integer convex program, where here we're using x sub c to denote continuous variables and x sub I to denote integer variables. And so to take the convex relaxation of C, we treat those integer variables as continuous. So for instance, if the x sub I belong to the set 0 or 1, we would relax that to saying that x sub I belongs to the interval 0 to 1 inclusive. And so it turns out that the convex relaxation of a hybrid zonotope is a set known as a constrained zonotope. So constrained zonotopes are defined here. So ZC here is a constrained zonotope. And one thing you'll note is that all of the inequality constraints in the constrained zonotope, so where this green box is, are box constraints. And we'll exploit this when we go to solve these convex subproblems, which are QPs in our mixed integer quadratic program solver. Okay, so now getting into our MPC problem formulation. So we have a quadratic objective, LTI dynamics. We additionally have polytopic state and input constraints, which we represent as constraint zonotopes in our formulation, but I won't go into detail on that here. We require that the outputs of the system lie inside a non-convex union of polytopes. So the outputs here are denoted as Y, and we require that the Y belong to some set F, which is the union of some polytopic sets Fi. So in this graphic on the left here, you can see that we have 12 polytopic subregions, right, that we are showing. And so the requirement is that the position states here are the output, and those have to lie inside the union of these Fi. And optionally, there's a cost associated with each of these polytopic regions Fi. So we would do this, for instance, for risk-aware planning. So for instance, if we wanted to penalize motion plans that pass through a certain region of the obstacle-free space. So we take that MPC problem and we formulate it as a multi-stage MIQP, wherein the hybrid zonotope constraints are applied at each time step K. So this multi-stage MIQP is defined as shown on the top left side of the slide here. So the cost and the inequality constraints are confined within a time step. So yeah, the cost and inequality constraints do not span time steps. And additionally, or conversely, the equality constraints can span one time step. So we're using a sparse formulation where we have the states, inputs, and convex constraint variables here as Z, and then we have additionally these hybrid zonotope factors that we need to optimize over as additional variables. And so what I'm just showing here is that on the right side of the slide is that the matrices and vectors that define the hybrid zonotope are just feed directly into the definition of the multi-stage MIQP here. So when we go to solve this multi-stage MIQP, as I mentioned, we're solving this more quickly by exploiting the hybrid zonotope properties. So for instance, we're exploiting that these hybrid zonotopes are tight. So this tightness property allows us to, in conjunction with some constraints that we're deriving from the autonomous vehicle motion planning context, create very tight QP subproblems. So what are those constraints that we're using from the AV motion planning context? Specifically, we're using what we're calling here a reachability constraint, where we use the max distance that the autonomous vehicle can travel in a time step of the MPC problem to get constraints on how the convex regions can be combined across time steps. So, for instance, we would say that region 5 here cannot be reached before time step k equals 5, or we're denoting the initial position of the autonomous vehicle with this green diamond. And then we would say that at least 8 time steps are required to go between regions 5 and 9. And that, again, that's based on the max distance the vehicle can travel in a time step of the MPC problem. So in our branch and bound framework, and this on the left here is just a sketch of a branch and bound algorithm. We use these constraints during node creation to identify binary variables that must be 0 due to the constraints. And this allows us to perform constraint tightening. And because the hybrid zonotope constraints have the property that their convex relaxations are tight, applying this constraint tightening allows us to generate very tight convex subproblems. Additionally, in many cases, this allows us to discard nodes that we know are infeasible a priori. So that's how we generate QPs. And then when we go to solve the QPs in the branch and bound framework, we take advantage of the fact that the inequality constraints are all box constraints. And so the way we do this is we use a multi-stage interior point formulation from reference 1 at the bottom of the slide here. And this particular interior point solver has the property that if all of the inequality constraints are box constraints, you can significantly reduce the number of matrix factorizations that you need to perform. And this allows you to solve the QPs much more quickly. Okay, so now getting into some simulation results. So we can see here we have 5 different examples, and in each case we're using a double integrator model. And at the bottom where the red squares are is the start point for the simulation, and at the top is with the green diamond or green star is the goal destination. And so at each time step of the simulation, we're solving a mixed integer quadratic program to generate the motion plan. And that motion plan is being represented by these red circles here. And then the actual trajectory taken by the system is given by the blue dots. So you can see that the MPC formulation and solver are able to navigate the double integrator model through the non-convex obstacle free space. So the left 2 most examples here are polytopic maps, where we're using a vertex representation to hybrid zonotope scheme to get the hybrid zonotope representation. Maps C, D, and E are all occupancy grid maps. Map C is a binary occupancy grid, and map D is a occupancy grid where we have spatially varying cost. So in this case, to do risk-aware planning is the idea. So squares that are more dark red are more bright, right, are higher cost, and then squares that are more white are low cost. And then map E is a 3D example. So we are solving these mixed integer quadratic programs much faster than state-of-the-art solution approaches. So typically by an order of magnitude. So these bar graphs here give solution times for our solver. The top set of bar graph or the top set of bars is the average solution time over the course of the simulation. And then the maximum solution time is given on the bottom set of bars, and that's the max solution time of a single iteration over the course of the simulation. Each of these 5 sets of bars corresponds to one of those maps that I showed on the previous slide, so to those different simulation examples. And those are given on the bottom of the slide here as well. The blue bars all correspond to our solver, and the red bars correspond to Gurobi, which is a state-of-the-art general purpose solver. The dark blue bar is our solver with hybrid Zonotope constraints. So that's what HZ means here. And the sort of purplish bar is our solver with HREP or half space representation constraints. And the union of those HREP constraints is taken using the big M method. And then Gurobi, we compare against using the exact same formulation. So we pass the problem to either our solver or to Gurobi. And so the dark red set of bars is Gurobi with hybrid Zonotope constraints, and the lighter red set of bars is Gurobi with HREP constraints. And then the leftmost set of bars is our solver with hybrid Zonotope constraints using binary variable worm starting, which I won't go into here, but it allows us to solve the optimization problems more quickly in an MPC context where we have similar optimization problems between time steps. And right, so as you can see, our solver always solves the optimization problem more quickly than Gurobi, usually by an order of magnitude. And our solver is always faster using hybrid Zonotope constraints than using HREP constraints due to its structure exploited construction. Gurobi, on the other hand, is sometimes faster with hybrid Zonotope constraints and sometimes faster with HREP. Some parameters for these results are solver is implemented in C++, and we're calling Gurobi via its C++ API. Using a desktop with an i7 processor, double integrated dynamics model, 15-step MPC horizon, same convergence criteria for both cases, for our solver and for Gurobi, and both solvers were configured to use 16 threads. So how are we solving these optimization problems as quickly as we are? First, due to the tight convex relaxations, our solver is converging in fewer branch and bound iterations using hybrid Zonotope constraints when compared to HREP. So this bar graph here is proving what I've said before, which is that tight relaxations allow you to converge in fewer iterations. So the top set of bars is the average number of branch and bound iterations over the course of a simulation, and the bottom set of bars is the maximum branch and bound iterations of a single MPC iteration over the course of the simulation. And throughout our solver, using hybrid Zonotope constraints is convergent in fewer iterations than the same solver using HREP constraints. Additionally, we are able to solve the QPs that we're generating in our branch and bound formulation more quickly using hybrid Zonotope constraints. And this is because we're using that QP solver technique where the box constraint structure can be exploited to reduce the number of matrix factorizations that need to be computed to solve the QP. And so you can see that in particular for the occupancy grid maps, we are solving the QPs much more quickly using the hybrid Zonotopes to represent the obstacle free space. So we're able to solve these problems as fast as we can because we're converging in fewer iterations, and those iterations are faster. Additionally, empirically, our approach scales well with increasing MPC horizon. So these bars give average and maximum solution time as before, but the bottom, the x-axis is increasing MPC horizon from MPC horizon of 5 steps to 20 steps, going from left to right. And as you can see, our solution times are staying low as MPC horizon increases. They are increasing, but not particularly quickly, especially when compared to HREP constraints and to Gurobi. So in summary, by exploiting the structure of a hybrid Zonotope constraint representation within an MIQP solver, we can efficiently solve MPC motion planning problems for autonomous vehicles. We also have also included in our journal paper submission is some processor in the loop results for real-time implementation, which I won't go into here, but we've implemented the solver in ROS2 context on an embedded processor and saw good results. Additionally, we have a conference paper submission that demonstrates region-dependent constraints and we are currently working on validating these methods experimentally using ground robots. So thank you.